Thank you to the organisers for organising this and for letting me talk to you about this. So this is based on a recent paper with my supervisor, Peter Kravchuk, and yeah. So it's looking at defects, and in general, when we take a CFT and we insert a conformal defect, we expect this to break the conformal symmetry of the theory, and we expect it to break it to the group that preserves the location of the defect. So if we start with the Euclidean d-dimensional conformal group and we insert a p-dimensional defect, we expect this to be broken to the conformal symmetry along the defect and rotations around the defect. Is there any way I can move this? Hopefully that works. Okay, that'll do. Yeah. So you can see if we've got a codimension 2 defect, that means we've got rotations around it, and we've got conformal symmetry along the defect. So what we wanted to look at was, can you insert such a defect that we preserve conformal symmetry along the defect, but you don't preserve rotations around the defect? Some examples of this are known, like Gukov-Witten defects and vortex loops in ABJM theory, but we wanted to find an example of such theory where we can do this, which doesn't involve supersymmetry and is just a bit simpler to deal with. Yeah, and one thing we expect is when we break this symmetry, we should get some kind of a tilt operator to parameterize this breaking, analogous to the way that breaking symmetry under translations gives us a displacement operator. So we do indeed construct such a theory, and we do so in the critical O2N model. We write this in terms of n complex fields with a quartic interaction, and then we start by inserting a monodromy defect into this. So what that means is we take a codimension 2 submanifold, and we say that every time that we rotate around a defect, our fundamental fields have to pick up a phase. We parameterize using these kind of coordinates with theta as a coordinate around the defect, and we say that every time that we increase theta by 2 pi, we have to pick up a phase, which we write as e to the 2 pi iv, where v is a number between 0 and 1. All been studied before, for example, in this paper by Giombi et al. And we know about the operators in this theory. And one interesting thing is that because our fields are no longer periodic under increasing theta by 2 pi, you don't get integer spin operators, you get operators with spin in the integers plus v, so that it picks up this little phase as we go around 2 pi. And we know the scaling dimensions of these operators. These are plotted at large n. And what you can see is that we do, in fact, have some relevant defect operators on here. So you have a spin v operator, which is relevant for v less than some parameter, which at large n in v equals 3 is roughly 0.618. And you've also got an operator with spin v minus 1, which is relevant for v greater than 1 minus that. And we know what this threshold is in large n in 3 dimensions and also in 4 minus epsilon at any n. So the idea that we had essentially was, what if we look at the RG flow triggered by this operator and see what CFT we can get in the IR of that flow? So we add to our action some coupling times the real part of that integrated along the defect, and we call the thing that we get a monodromy pinning defect. So think about the symmetries of this. And if we start with no defect, obviously we've got conformal symmetry and we've got an O2N internal symmetry. If we insert a monodromy defect, then we break this to the normal defect conformal group of transformations along the defect and rotations around it. We can no longer treat it as real scalars, because to pick up our phases, we have to work in terms of complex scalars. So our symmetry group gets broken to UN. And then when we do this RG flow, we also, because this field that we're triggering the RG flow by has non-trivial transverse spin. We now break symmetry under rotations around the defect, and we have to pick one of the fields to trigger it by. So you also break our symmetry there from UN to UN minus 1. There is, however, a symmetry which is a combination of these broken generators. So of the SO2 here and of the UN here, which is essentially when you do this, you rotate around, and because this field has spin, it will pick up a phase, but you can use an internal symmetry in here to pick up the opposite phase, so that you still get symmetry if you combine these two. So it's worth noting we do break rotations, but we break the internal symmetry and the rotations in such a way that we keep an U1, which is a combination of the two. So we've got a parameter V now, which we can look at this theory in, and we can look at it in different dimensions. So you've got this threshold V equals V star, where this our G flow makes sense, where our operator is relevant, and we can study this at any point underneath this curve. And there are various expansions we can look at this in. And in this paper that I'm talking about, we do indeed look at this in various expansions. We look at it in a large N expansion, which should be valid everywhere here. But we also have various methods we can do at finite N to look at this. So, for example, we have a 4 minus epsilon expansion, where we can look at this in the neighborhood of 4 dimensions, where our bulk coupling becomes small. We have conformal perturbation theory, because as we approach here, our operator is only marginally relevant. Along this curve, our field, our perturbation is irrelevant, so we should just get back to a monodromy defect. And we also have this point here where we didn't introduce any monodromy, and we're in 3 dimensions, where we just get a known defect called the pinning field defect, which just corresponds to integrating one of our real fields phi along the defect. So what we can do is we can look at our theory in all of these various expansions, and we can see how they compare and check that everything makes sense. And we do indeed do that in a few of these expansions. So first of all, we can look at conformal perturbation theory. So the idea of this is, sorry, that's meant to say for V approximately equal to V star. So essentially the point is, as we approach this threshold, the operator is only weakly relevant. And so we can write scaling dimension. We've got codimension 2 defect, so its scaling dimension must be d minus 2 minus a small parameter delta. And if we expand our beta function out and we assume there's a quadratic term, then we can solve this to find the root, and we can find that it must have a root here. And so indeed, we're supposing we can approach this as a parabola, as a quadratic function. And so what you can see is that the gradient of our beta function here is minus the gradient of our beta function here. And so what you should get is that the anomalous dimension should be opposite. So if we can approximate our beta function in this way, you should get that our scaling dimension looks like d minus 2 plus delta. However, that's not what we see. So why? The answer is because, in our case, this quadratic term has coefficient 0. So in fact, we have to go to the next order. And our beta function looks more like this, with 2 fixed points for a negative and a positive value of the coupling. And you can indeed find where our fixed points are and the gradient here. And what you find is that our scaling dimension, instead to leading order here, is d minus 2 plus 2 delta instead. The reason for this, it turns out, is because in conformal perturbation theory, this coefficient here comes from a 3-point function, which has to be 0 by the symmetries of our theory. So we then look at this in other expansions. So we look at it in large N, and we do so using fairly standard techniques other people have used for defect CFTs. So in particular, there are these 2 papers by Giombi et al. And by Cuomo et al., where they use this to study monodromy defects and pinning field defects. And essentially the way they do so is they perform a useful Weyl transformation. So if you take our metric in the coordinates that we introduced here, and you divide your metric by a factor of r squared, then what you get is a metric for S1 and a metric for ADS d-1 in Poincare coordinates. The defect is located at r equals 0, so our defect is now at the boundary of ADS, which lets you use all sorts of useful ADS CFT techniques to look at things like scaling dimensions. What this means is that adding our defect term just corresponds to changing our boundary conditions in ADS, and then we can do a lot of standard large N techniques like a Hubbard-Stratanovich transformation, and we can saddle expand to get a large N expansion. So we can then look at this theory, and what we do is we look at a particular two-point function of an operator which is roughly phi squared, and we decompose this in a spectral representation, so in a basis of Laplace eigenfunctions on here. And what you find via ADS CFT stuff is that we can find the scaling dimensions of various different operators that are exchanged in this two-point function. And we do indeed find an operator which corresponds to the operator we're perturbing by in conformal perturbation theory. We find another operator, which is the displacement operator, and we find a third operator, which we call S minus, which also is known to appear in the various limits this coincides with. So in monodromy defects, in pinning field defects, there are some quite nice things. So if you think about the case where v equals a half, the phase that we're picking up is a factor of e to the pi I, so -1. And so that just means as we go around the defect and monodromy defect, we just pick up a change of sign. And so you actually get a bigger group of symmetries preserved. And you can see at that point, the scaling dimension of this operator to leading order in large N seems to be 2. You also get that the one-point function of phi has a nice expression. I think it's just an integer times some factors of pi. And so the theory you actually get quite interesting data out of that at that point. But we can calculate this at all values of v at large N. And we can indeed compare it to the conformal perturbation theory prediction. And we do indeed find that in the limit, as this becomes irrelevant, it does behave as we would expect it to. So these limits seem to commute. So finally, we look at this in 4 minus epsilon as we approach here, and the bulk coupling becomes small. It's a bit hard to study this because the defect coupling is still large, so there are limits to what we can do. But one easy thing we can do is we can just look at the profile of phi I, and we can say we know its classical scaling dimension, we know its monodromy has to be this, and so let's try to constrain the coefficient here by the bulk equation of motion. And indeed, what we find is that this coefficient must be given by this expression. And once again, in the limit of large N, this is something that we can extract analytically, and we can find that indeed this seems to agree, which is all good. Yeah. So yeah, we can look at this defect in a bunch of different pictures. And we can extract various things. And it's quite a nice family of defects because if you think about most of the different kinds of defects you can look at in the O2N model, this corresponds to them in some limit. So you've got your pinning field defect, you've got your monodromy defects, and you've got a huge number of other defects. And in particular, you've got a continuous parameter you can tune to look at different ones of these theories. And so there is a limit where essentially you've got both that your bulk coupling and that your defect couplings are small. So you're in the 4 minus epsilon region and the conformal perturbation theory region. And there you should be able to do everything just via naive perturbation theory. And it'd be interesting to see what you can do with that. See whether this can correspond, if you look at that at various orders, see if that can reproduce what we get here in the pinning field defect in 4 minus epsilon. Also, you can obviously look at higher orders in 4 minus epsilon. It would also be interesting to see if we can get more of these spinning defects, because by and large, we tend to just look at defects as things that preserve rotations around the defects, but there's no reason that they have to. And in particular, in some previous work, we found that in 3D, if you insert a defect into a CFT, you can get a non-trivial Weyl anomaly, which is very nice. And so it'd be really cool if we could actually find a theory where this particular term appears. And that's something I would like to explore in future work. Okay, that's all. So does anyone have any questions?
Alex, so we'll do questions, but let's just wait till the microphone gets passed around. Oh. Okay. Any questions? Yes.
Yeah. Have you considered defects whose world lines are like null rather than timeline?
So all of this we just do in Euclidean signature.
Okay.
So yeah, this is just a generic one in there. Yeah. So we haven't considered it, but I'm sure you can.
Do you know of any experimental implications of these results at critical points?
Yeah, well, so experimentally there are realizations of monodromy defects when you've got some sort of misalignments in spins in an O2 model kind of system. So you get that kind of thing. And since this is an RG flow that can flow from there, it means in principle, if you're looking at one of these systems with such an impurity, you should check that you're actually getting the monodromy defect impurity and not this, because they look very similar. They both have this topological surface attached to your defect. And yeah, no one's really talked about this before. So I think it'd be interesting to look at those experimental things and check that you are actually getting a monodromy defect and not this.
What might pick out the value that you called V in that setting?
So I guess in monodromy defects in these things, you tend to, if you think about particle vortex duality for the O2 model, you can think of a monodromy defect as having some kind of a surface with some charge associated to a U1 gauge field around it. And so it's connected to that charge. So in this case, I guess that's what that would correspond to. Yeah, I think so.
Thank you.
Any other questions?
I will also say you can also construct this on the lattice and stuff. Yeah, that same kind of thing. Just look at the setups people have used to look at monodromy defects on this and essentially combine what you do to look at an impurity along a line on there and a monodromy defect, and you should get this. And that all seems very possible to do.
Did you think about bulk marginal deformations? Away from the defect? It's still preserving the conformal invariance?
No, I think other people have, but no, we haven't.
And the other question I had was, so as you varied new, there was points where you seem to get exactly, you get additional marginal operators. Did I get that correct when they went to deltas too?
Sorry, do you mean just in the monodromy defect model or in the IR thing?
This one. And so when it goes down.
So the defect is one-dimensional in 3D. So marginality is just this line.
Oh, sorry, got that wrong.
Yeah. Okay. Yeah, there is the interesting point where v equals 0.5, where you get another operator with dimension 2. We don't think that's because of the symmetry. We think it's just a large N artifact. And so that also means you should be able to study this, well, probably at large N analytically, in the case where v equals a half, because we expect there to be a reason it's 2. But yeah.
Good. Okay, so thanks. Oops, one more question. Maybe more than one.
Yeah, thanks for the talk. I was just wondering, do you have any hope for a controlled 4 minus epsilon expansion beyond just the ansatz that gave you the leading order?
Yeah, so it's difficult because it's not weakly coupled. So naively, no. I mean, you can try. We've got that region where the coupling is marginal, and maybe you could do some kind of resummation there. to try to get it away from marginality. We don't have a particularly concrete plan for it, which is why we've not done it. But people have managed to do it for the pinning field defect in 3D. But that involves looking at a 4 minus epsilon expansion where it flows to a line defect in 4D. And we can't do that with monodromy defects. They have to be codimension too. So we can't directly use what they do. So maybe in some way, but it's not a particularly obvious way to do it.
No, I see no more questions. So let's thank Alex again for a nice talk.